resistance and magnetic leakage. First, we will start with resistance. We consider the transformer with resistance and without magnetic leakage. Transformer with resistance. Magnetic leakage is considered to be negligible or it is neglected. Leakage neglected. But obvious, your transformer, primary and secondary would have certain resistances. Let R1 be the resistance of the primary winding, R2 be the resistance of the secondary winding. V1 applied voltage, let N1 N2 be the number of turns of primary and secondary winding. E1 and E2 are the self-induced. Let phi be the magnetic flux in the core. V2 be the secondary terminal. When the distance in the winding, there will be the difference in the terminal voltage and induced EMF. Your V1 would be equal to E1 plus, if I1 is the current in the primary and I2 is the current in the secondary, I1 R1 and V2 will be the E2 minus I2 R2. Drop across the resistance of the winding, rest we will get the across the terminal. We apply the voltage V1, drop across the armature primary winding, then E1 will be the back EMF. Now, if we draw the phasor diagram of the transformer considering the resistances, then first draw the phasor diagram for no load of the transformer. Phasor diagram for no load. E1, E2. And this one is V1, this one is I0. Now we have considered here, this was the case where we have considered the transformer neglecting the lossage, either iron lossage or copper lossage. Now this side may be represented by E1 because your one thing is clear, this E1 and E2 would be in same phase, and V1 is the sum of this one, phasor sum, and V2 would be the phasor difference of E2 and this one. So how will represent on this particular phasor diagram? For example, on the primary side, let start with the secondary side and assume that your load is a pure resistive load. In a pure resistive load, your voltage and current would be same phase. Another is V2 is E2 minus I1 I2. Let this be the V2. Now keep it E2. This be the V2. And voltage and current are in same phase. Drop across the resistance will be in phase of the current I2. In case of pure resistance, voltage and current are in same phase. The drop across this I2 R2 and I2 are in same phase. So they are represented by, they are just I2 R2, and that would be equal to E2. That means we will represent this here V2, this will be the I2 R2, and this will be the I2, because both are in same phase. Voltage and current, this I2 and I2 R2 are in same phase, V2 and I2 are in same phase, and E2 is this phasor sum of V2 and I2 R2. E2 is sum, or this V2 is different of E2 and I2 R2. Now, counterbalance current I1 dash is in phase opposition of I2. Resultant current I1. Now, voltage drop across this resistance and current are in same phase. So draw a line parallel to this I1 R1, and this will be the voltage V1. Having the, this is the phi naught and this is phi 1. So this will be the case where the load is a pure resistive load. You will get better understanding. Let us draw for the inductive load. For inductive load, phi I naught, let this axis be represented by E1, and this we have to represent it by E2. In case of inductive load, your current lags the voltage V2. Means this is current I2, it will lag the voltage V2. And this I2 R2 will be in phase with current I2. The voltage drop across this, then we have to represent this like, let it be V2, and this would be the I2 R2, and this will be the E2, and this angle will be phi 2. Both I2 R2 and I2 are in phase. I2 lags V2 by phase angle of phi 2, and E2 is the phasor sum of V2 and I2 R2. E2 is phasor sum of V2, I2, R2, or V2 is difference of E2 minus I2, R2, phasor difference. Now, come to primary side, I1 dash in phasor position to I2, counter, just at an angle of 180 degree. I1 phasor sum. Now V1 drop across this resistance, let it be denoted by I1, R1 and this will be the V1. Now you can represent the angles. This is V1, this is phi naught, this is phi 1 between I1 and V1. So this would be the phasor diagram when your current I2 lags the applied voltage, secondary terminal voltage V2, or your load is inductive load. Now again let draw for the capacitive load. Let the load is capacitor. Minus E1. So your current would lead the voltage. Let this current be of leading nature, I2. Let this be denoted by phi naught. V2 leading, let this be V2. Voltage drop across resistance R2 and this I2 would be in same phase. Means I2, R2 will be represented parallel to this line. I2, R2, and this will be the E2. Now this angle will be the phi. I1 dash phasor position counterbalance current which neutralize the secondary induced flux or secondary flux, so that your phi flux is maintained in the core, or it neutralize the demagnetizing of flux phi 2 developed by the current I2. Now this is the current I1. Your I1 and this is parallel to this. Parallel to this would be this I1, R1, and this I1 will be same phase. So this will be the voltage V2. So we can voltage V1. So this will be the phi 1. This will be the phi naught. So this is the phasor diagram when your load is capacitive, means your I2 leads the voltage V2 by an angle of phi 2. Now we have considered these resistances on both the sides. Primary side resistance is R1, secondary side resistance is R2. These resistances may be transferred on either side. For example, we have connected the apparatus on this side, so So we require the resistance of this side for our calculation purpose. Then we can transfer these resistance on this side, so that we are calculating, or we have the device measurement on the secondary side. So our requirement is to find the equivalent resistance of all the transformer on this side. So we can refer these resistance on secondary side. In such a way, during referring, percentage of voltage drop should remain same. For example, let this R2 is being referred to the primary side. So what would be the total primary resistance on the primary side? It would be R1 plus this resistance R2 is referred to the or transferred to the secondary side. So its equivalent value on the primary side would be R2 dash. Means if we see the winding, we see resistance R1 and we have transferred this resistance R2 and its equivalent value is this one. So that resistance we have transferred on this side, primary side. Then what we said, the resistances would be transferred in such a way that percentage of voltage drop should remain same. For example, we have transferred this resistance on this side. So what is the voltage drop here? I2 R2, and percentage of voltage drop is divided V2 by 100. This will be the percentage of voltage drop. That should be equal to, now this resistance R2 is transferred to the primary side. So here current is I1 and its equivalent resistance is R2 V2 100 or V1, or your R2 dash would be equal to V2 by V1 into I1 by V1 by V2 into I2 by I1, or 1 by K square R2. Where K is transformation ratio is V2 by V1. So in such a way, its equivalent value will be R2 divided by K square. Likewise, we want to transfer this resistance on this side. So what would be the equivalent resistance? On the referring to the primary side, R1 plus R2 by K square. Now we want to transfer this resistance on this side. Let's see what happens. What we said, percentage of voltage drop should remain same. So R02 is R2 plus R1 dash. So we have transferred this R1 on this side. R1 dash R2. So its equivalent resistance on secondary side would be this, and this will be transferred in such a way that percentage of voltage drop should remain same. What is the voltage drop due to this resistance R1 on the primary side? R1, and what will be the drop when this resistance is being transferred on the secondary side? This resistance on the secondary side is denoted by R1 dash. What is the current on the secondary side? I2. What is the voltage? V2. So your R1 dash would be equal to V2 by V1 I1 by I2 into R1, or R1 dash would be equal to K square R1, where K is transformation ratio and given by V2 by V1, or R02 would be equal to R2 plus, so we can transfer our parameters which resistance is on either of the sides. Now we have considered the resistances. In actual transformer, you can't ignore the magnetic leakage. Transformer with magnetic leakage. What is magnetic leakage? We have considered this transformer, but we said when an alternating voltage is applied to the primary side, magnetic flux is established in the magnetic core and EMF will induce in primary as well as secondary winding. There are certain flux which links with only one winding, phi L1, phi L2, and this leakage flux is induced due to the ampere turn balance on the or magnetic force on the primary side, whereas this leakage flux phi L2 is due to the flux developed due to the magnetic force on the secondary side. On the secondary side, some flux is established in the core which created the demagnetizing effect, whereas some links only with that passes not through the core, that through air. That flux is known as leakage flux. Now these leakage flux induce certain EMF that may be termed as on the both side EL1, EL2, self-induced EMF due to primary magnetic force, EMF induced due to self-induced EMF due to secondary magnetic force, EL1 and EL2, and this EMFs may be considered a drop across the coil. This EMF is termed across the voltage or loss or voltage drop across the same coil, and that is done by reactance. Which causes the voltage drop across the primary winding XL1, XL2 causes the voltage drop across the secondary winding. Now, likewise, we transferred resistances on either sides. We can transfer these reactances on either side in such a way that percentage of voltage drop should remain same. For example, this reactance referring to primary side, that will be denoted by XL1, or we can, and this is, let it be XL2. So this will be the XL1 and secondary reactance is transferred to the primary side will be denoted by XL2 dash. Let this be the primary current, this be the secondary current, and it should be such that we can transfer these reactances on the either side in such a way that percentage of voltage drop should remain same. On the secondary side, primary side, what is its voltage drop? I1 XL2 dash divided by V1 into 100. On the secondary side, what was its drop? I2 XL2 V2. Or XL dash would be equal to V1 by V2, I2 by I1 XL2, or this will be XL2 by K square, where K is V2 by V1 or I1 by I2. Means we have transferred the reactances of the primary side. XL1, XL2 dash. Now what would be the X01? XL1 plus XL2 by K square. Likewise, these reactances may be transferred on the primary side. On the primary side, on the secondary side. On the secondary side, the total reactance will be represented by XL2 was the secondary side reactance and primary side reactance refer to secondary side, and that will be in such a way. What is its value on the secondary side? I2 percentage of voltage drop should remain same. What was its percentage of voltage drop on the primary side? I1 XL1 V1 into 100, and XL1 dash would be equal to V2 by V1, I1 by I2, XL1, or XL1 dash primary reactance referred to the secondary side would be K square XL1, where V2 by V1 is K, transformation ratio or I1 by I2 is K. Therefore, X02 will be secondary reactance plus K square XL1. So we can, like resistances, we can transfer these reactances on the secondary side also. So we can just transfer these parameters on the other side. So we will consider these resistances and these magnetic leakage of the transformer simultaneously, and then we will draw the Phasor diagram for the actual transformer. Now we will consider a transformer with resistances and magnetic leakage. Now let us consider the transformer with resistances and reactances. Let R1, so let this be the primary side reactance be denoted by X1. R2 in place of XL1 we represent it by X1. R2, X2, E2 with the induced EMF, V2 with the terminal voltage, and if your load is connected, current will flow through the circuit. Let E1 with the primary voltage, primary induced EMF, V1 with the alternating voltage applied, I1 with the primary current, which is phasor sum of counterbalance current and no load current. Now, what would be the V1? What would be the relationship between V1 and E1? E1 would be V1 minus drop across this primary winding, and this R1, it would be Z1, Z2. So it would be E1 plus I1 R plus JX1, or E1 plus I1 Z1. So this would be the E1 plus this is equal to V1. Whereas V2 would be, what would be the V2? E2 plus minus this one. E2 minus I2 R2 plus JX2, or E2 so it will be this. Now draw the phasor diagrams. Or one question here arises, you know transformer cannot be used in DC because we require the change of magnetic flux. In case of DC, no change in magnetic flux, no EMF would induce. Another question, what happens if you apply the same DC, rated DC to the transformer? What happens when you apply rated DC? For example, on primary side, you apply rated DC. So what happens? This one V1 minus E1 is I1 Z1, or I1 is V1 minus E1 by Z1. Now when you apply DC, there will be no induced EMF, no back EMF. So this back EMF would be 0, and this will becomes V1 by Z1. For example, you have a 220 volt applied voltage and back EMF was 210 and the impedance of was 1 ohm and the current was 10 ampere. If it becomes 0, the current would becomes 220 ampere. So your winding would not be able to sustain that current or to bear that current. its insulation will fail and the winding will burn out. Primary of the transformer would burn out due to heavy current. As there is no back EMF, this causes the large current in the primary winding and your primary of the transformer would damage. When you apply DC, transformer didn't work, and in addition to its work, its winding would be damaged. Primary winding of the transformer would be damaged. Now, let us draw phasor diagram. So we can transfer these parameters on either side. If we transferred it on the primary side, so your Z1 node would be equal to Z1 plus Z2 dash. That is, Z1 is R1 plus JX1 plus R2 dash plus JX2 dash. We have already discussed this, how we can transfer it. We can transfer it just, we transfer resistance on the primary sides in such a way that percentage of voltage should remain same. We have already discussed. Likewise, we transfer these reactance and then we will find out the equivalent impedance. So what would be the R01? Basically, this would be R01 X01, and R01 is R1 plus R2 dash, and X01 is X1 plus X2 dash. Likewise, impedances can be transferred on the secondary side. Z2 plus Z1 dash, R2 plus JX2 plus R1 dash plus JX1 dash, or it would be R02 plus X02, that is R2 plus R1 dash plus JX2 plus X1 dash. This thing we have already discussed earlier in case of when we transfer these resistances and reactances on the either side. Now, important one, how we will draw the phasor diagram. We have discussed the phasor diagram neglecting your resistances and magnetic leakage. If in examination the examiner says draw the phasor diagram of the transformer neglecting the resistances and magnetic leakage, then you can draw the phasor diagram. If he says draw the phasor diagram of the transformer, then you have to draw the phasor diagram of actual transformer, that is considering magnetic resistances and magnetic leakage. So first method of drawing the phasor diagram would remain same. Because these E1 and E2 would be in same phase. These E1 represent on the phase opposition. Minus of E1 would be in phase opposition of E1. This is flux I naught, no load current. Phi 1 naught we will represent once we find the V1. We know V1 is E1 plus I1 R1 JX1. One thing you reminds here, I1 R1, that voltage drop across this resistance would be in phase with this I1, and voltage drop across this inductor, that is I1 X1, would be lead this current I1 by an angle of 90 degree. across pure inductor, this coil is termed by the inductor. Across pure inductor, current lags this voltage across this inductor by phase angle of pi by 2. Now, when you have a pure resistive load is pure resistive, one thing is clear, your V2 and I2 would be in same phase. V2 and I2 would be same phase. So how you will represent it? Let this be V2, I2, both are in same phase. Now, voltage drop across resistance. This is R2. Voltage drop across this resistance. I2, R2 is in phase with I2. And voltage drop across this inductor I2 X2 would lead the current I2 by phase angle of pi by 2. So it will be perpendicular. So this drop is, so this will be your E2 and this will be the I2 Z2. This phase angle phi 2 is 0 between voltage and current, and this will be your resultant voltage. Now come to the primary side. Counterbalance current I1 dash is in phase opposition to I2. I1 is phasor sum of I0 and I1 dash. Now drop across resistance I1, R1 would be in phase with I1. Both would be same phase. Phase angle between I1, R1 and I1 would be 0. तो ये हमने रिप्रेजेंट कर दिया I1, R1 और ये मान लीजिए फेजर ड्रॉ कर रहा है I1. Both are in same phase. We have represented here. I1 X1 perpendicular to this, and this will be the I1 Z1, and this will be the your voltage V1. So this will be the phi naught, this will be the phi 1. So this will be the phasor diagram when your load is a pure resistive load. All things are the primary resistance and reactances are represented, secondary resistance and reactances are represented, and that is the resultant impedance. Now, in case your load is inductive, your current lags this voltage V2 by phase angle of phi 2. What will be the phasor diagram? Again, first draw phasor diagram for no load condition. We have represented phi. This is minus E1. Let this be the E2. Now, current lags the voltage. Let this be the V1, V2. Let this be the I2. First, draw the no load current. Let this be the I load. This angle be phi naught, phi 2. Now voltage drop across the resistance I2 R2, each I2 R2, which is in phase with current I2. Voltage drop across this and this current would be same phase. Voltage drop across this and this current have the phase difference of 90 degree in which your current lags. Let this be the 90 degree representation denoted by I2 X2, and this will be the E2, and this will be the I2 Z2. Now on the primary side, your counterbalance current would be in phase opposition of I2. Your resultant current would be I1, that which is the phasor sum of I1 dash and I0. Now voltage drop across this resistance is I1 R1, which is in phase with I1. So this drop will be indicated parallel to this I1 R1, and your I1 X1 is having a phase angle of 90 degree. This will be your I1 Z1, and this will be your voltage V1. Now angle between I0 and V1 is phi naught. Angle between V1 and I1 is phi 1. So this is the phasor diagram for a inductive load, when load is connected is of inductive nature. Now if the load is connected is of capacitive nature, means your current I2 leads V2. What would be the phasor diagram? Again, first draw the phasor diagram for no load condition. Let this be represented minus E1, which this be E2. Let this be the phi. Now let this be the secondary voltage V2. We have selected it arbitrarily. I2 leads V2 by phase angle of phi 2. Then your representation, your current I2 R2, drop over resistance, and this current I2 are in same phase. This will be I2 X2, and this will be the E2, and this will be I2 Z2. Now on primary side, your counterbalance current is phase opposition of I2. I1 dash, and your primary current I1 is phasor sum of I0 and I1 dash, and your voltage drop across resistance is in phase with current I1, So this is represented I1 R1. It would have a phase angle of 90 degree. I1 X1, voltage drop across inductor, this will be I1 Z1, and this will be the applied voltage V1. Now indicate your angles phi naught, phi 1. So this will be the actual phasor diagram in loaded condition when the load is of capacitive nature. Means your I2 leads V2 phi 2. So if in examination it is mentioned that you have to draw the phasor diagram, then you have to draw the phasor diagram of a loaded transformer without neglecting resistance and magnetic leakage. Means by considering the resistance as well as magnetic leakage. If it says draw the phasor diagram neglecting this, so we have already discussed, then you can draw that particular phasor diagram for the transformer. This is the phasor diagram of the actual loaded transformer. Now we can transfer these parameters on the either side. For example, let us transfer these on the primary side. So what would be the resistance? R01. Equivalent resistance would be R01. And this R01 would be equal to, and your impedance referring to primary side Z01 will be R01 plus J. Equivalent reactance referring to primary side, equivalent resistance referring to primary side. Or what is this R01 here? R1, R2 dash. This secondary resistance referred to primary side. We have already discussed that particular thing. How we will find out the equivalent resistance referring to primary, secondary resistance equivalent to primary side, we will find out. Likewise, we can transfer these parameters on the secondary side. R0, equivalent resistance and equivalent reactance. We will transfer these resistances and reactances on the secondary side. Z02 would be R02 plus JX0. Likewise, R02 is R2 plus R1 dash, X02 is X2 plus X1 dash. Likewise, this X01 is X1 is X2 dash. So we can transferring the parameters and we can find out the equivalent impedance of the transformer or equivalent